I'm going to be standing on the podium because I'm unprepared and I have my speaker notes up here, so apologize about that, and I might kind of look over. But today we're going to talk about Icewine, Redis microcontrollers, and setting fire to your desk. These are all, strangely the thing that is the most fictitious is the Icewine in all of these things. Well, yeah, you know, sometimes if you have too much Icewine, you might set fire to your desk. But what I'm going to do, I'll tell you a little about myself first. I live in Edmonton, Alberta. I lived there as of 4 days ago. I moved from the South, the US South, to Canada about 4 days ago. And then I immediately came here. But I've had a long connection with Canada, and we'll talk a little bit more about Canada up here, and that's Icewine comes into there. How this came up, so I had a client approach me and say, I want to build something that does this stuff with a microcontroller. Can you help me? And like most people, when they say, can you do something for me and I will pay you money, I say, yes, I will help you. I had not worked with electronics in about 20 years. I did it as a kid. And I had read a little bit about it, and I said, well, I'll learn this for this particular project. And so I did that project and gave them some recommendations and that sort of thing. And then I kind of just let it sit there. And when you work with microcontrollers, the thing about it is that you get a lot of stuff. When you're software, you just download things. When you're working with physical hardware, you have to order all this stuff, and it comes to your house, and it's great because you get packages every day. And so I was sitting there, and I was working on Redis, which is what I work on probably 20 hours a week. And then I kept on looking over at my microcontroller and electronics station and going, I wonder if I could put these two together. And that's how this came about. So yeah, let's talk a little about IoT and security, Internet of Things and security. These are famously things that don't really go together. There's been stuff that's been out there that's given a really bad name. In this presentation, we're going to use IoT. With that, I'm going to talk primarily about sensors, which means that you're sending data to a server rather than making something happen, although you could use a lot of the same things. But when you come to security, it's a really big deal. The interesting thing about IoT and security is, unlike a server, once it's out in the wild, you don't have control over it anymore. You may never get an upgrade on things. And that's really scary because if you administer any servers, you update and patch and do all these things, hopefully. And so if there's something bad happens, then you go in and you're the person responsible and you make it better. Well, when you have a toaster or a sensor, you don't have that opportunity. Famously, the Mirai botnet, has everybody heard of that? Yeah, I see a lot of nodding heads. Took out the Dean, I don't know how to pronounce it, whole service in October 2016. And those were all things where people had ordered like a camera, like a security camera probably from China on eBay or something. It had really bad security on it because it was running, some really vulnerable software on it, and there's never an update to it. And I think that they still haven't updated it, believe it or not. So let's talk about Icewine. I know this is an odd thing. And I based this presentation on an article I wrote on Medium, which I suggest you go look at it after the end of the presentation. We'll talk about it. It's up there. Icewine is a product that in cold regions in Ontario, they have actually a lot of vineyards, and those vineyards have trees, and you can get a harvest at the end when it's really cold. And I was listening to CBC radio, and this is where the connection where I was looking at one side of my desk and looking at the other side of my desk, I said, this is something I could do, right? And so this is something that I just kind of got in my head and I couldn't get out. And so it was kind of almost a thought experiment at first, and then I just kind of snowballed. So the problem with Icewine is that you have to harvest at particularly right temperature, and it's like 1 degree Celsius is your margin of error. Otherwise, it rots on the tree, or the other way, it's non-alcoholic. It doesn't freeze distillate. And so these Icewine producers, these vintners, they have to have these huge groups of people ready to harvest the grapes at any moment, so that they have like hundreds of workers just waiting for the right temperature, and they all descend upon the vineyard and they pick all the grapes. But that's really expensive to have a lot of people idle and things like that. And so when I think of problems where you have a lot of very specific small areas in which you can do something, I think about data. And so my mind, I said, what if you took and you put a sensor on every single tree, and you can go in and say, this tree is at the right temperature right now, I'm gonna harvest this tree, and this tree on the other side of the hill is at a different temperature, I'm gonna wait until it's ready to go. So that's where it is. So that's where I came up with this, and so I just became obsessed with it, and I just had to get it out. That's where we're coming in with Icewine. So it's been kind of the, it's been almost the motto of this, right? So IoT and Unix-based systems, this is where it kind of goes south a lot of times for people. You have a lot of IoT things run many different flavors, Linux, Unix, FreeBSD, whatever. They run full-size desktop operating systems on little single-board computers often. And then they do what they need to do, and then they send the data or do whatever you need to do on your toaster or whatever. The problem with it is that they're really complex systems, and as you know, there may be hundreds of different packages involved on a Unix server, and you need to make sure they're all up to date, and people find new vulnerabilities all the time. So it's a really complex thing. There's a lot of surfaces to it. It makes it hard to secure, as anybody who's run any type of server knows, that you kind of have to be on top of things, and there's always something that goes wrong, and you're like, I didn't know I was running this, but it evidently needs to be updated. And the other thing about it is, if you're running a single board computer, you have a lot of power. You actually have excess power. Years ago, I had a TiVo set up, and I found out I could telnet into my TiVo. And anybody could telnet into my TiVo at the time. So there's all these things that you don't even know they're on, and sometimes they're there for specific reasons, but they just introduce vectors of attack, right? So it's complex. And who's going to sit there and go, I want to update the packages on my TiVo, my toaster, my fridge, whatever. It doesn't happen, and that's the reality of products. So what if you could do IoT without an OS on the device? And that's ultimately what we're going to look at here. It doesn't really have to have one. When we think of stuff, I think we all kind of tend to think of things as like a client, whether it be a web browser or some sort of other app, and then a server. And those clients generally are somewhat on parity with the server. I mean, they're usually just a shrunk down version architecturally of the server. And when you're talking about something with IoT, you don't need much computing power, right? You're doing things like running a microwave. You're doing things like, delivering a sensor on a tree. So you don't really need a full OS. You don't certainly need a telnet server on your tree, right? So let's talk a little bit about these things. And I want to do some differentiations before we get into Redis. I'm going to talk about microcontrollers today, but I think many people get confused with single board computers. The most representative single board computer would be a Raspberry Pi. Everybody's heard of these. How many people own a Raspberry Pi? Almost everybody. How many people own a microcontroller dev board? Oh, most of you. That's great. So this differentiation might not be as necessary, but I think this was when I was talking to some colleagues, this is where they didn't know the difference. I'll still go over it though. Microcontrollers, the most common one you might think of is the AVR Arduino Uno system, and it's a little 8-bit microcontroller, maybe 16-bit, I don't remember off the top of my head. But it's great for doing little projects. So you can plug things in. It's very friendly to use. You jumper wires. It's a lot of fun. And they're getting children to do this, and I think that's fantastic. But microcontrollers are absolutely everywhere. I looked at my kitchen a few days ago and saw how many things I had that have microcontrollers in them. My stove, my microwave, my Instant Pot, my CO detector, like everywhere you look, there's probably a microcontroller somewhere, just a tiny, sometimes it's a little PIC microcontroller which has like 4 pins or something. So, they're everything. Generally, anything that has a lithium-ion battery in it has a microcontroller that is actually monitoring the charge system because, they have a tendency to go bang, which is not related to my desk fire, which I'll get to at the end. So microcontrollers are different because they lack all the extras that computers do. They're a processor. They're generally self-contained. They don't have frame buffers, so you can't hook a monitor up to them and do a presentation. They are usually on a single chip or module. There's not a lot of other ancillary components on it. And single board computers are the other way around. They're just a small computer. That's all they are. And finally, you look at the cost on a single board computer. Raspberry Pis are pretty cheap, $30. Compute modules like $9 or something. And microcontrollers are, I like to say that single board computers are affordable, microcontrollers are cheap, down to like 1 cup of coffee equals several microcontrollers on a scale of someone going out and buy them, not even at like any production run discounts. So what we'll talk about today and what I'm using is the ESP8266. How many people have heard of the ESP8266? 3 people, okay. And this is one of the circuits I built. Real simple guy. This is a dev board, right? So this has a few things in it. If you see this little silver guy here, that's actually the computer. And the rest of the stuff does things like, voltage matching and a few other little things. This is a UART chip that allows you to hook it up to like the USB up here. And then it's got all these GPIO pins and some other little things here. This one's called a low-LAN. This is a really inexpensive one. So yeah, they're very different, the Raspberry Pi and ESP8266. So don't get them confused, and we'll talk about the things on this, but don't think I'm running a Redis server on this, please, because it's not going to work. So let's take a look at the size difference, and we'll talk a little more contrast here. You can see I've kind of got an outline there. And then you see the little ESP module, and then you see a Raspberry Pi, and they're scaled appropriately, so you see how different they are in size.
So you are running the Redis server on the Raspberry Pi?
I could, and that's actually interesting and challenging too. Salvatore did some recent work on that, but you certainly could run that, because if you look at the stats, right, the Raspberry Pi 3 has a gig of RAM, it's got 1.2 gigahertz quad-core processor, and let's just say the ESP is more constrained. So let's look at this. It has a different architecture than what you're used to. It's got a pure Harvard architecture on it, 64K of instruction RAM and 96K of data RAM. They're separated on the architecture there. 4 megs of flash. It's got 802.11b in, and it's $1 to $15 depending on the dev board that you're on. But just the module itself is in quantity down to 50 cents, right? So pretty cheap. The great thing about it too is instead of just going and running Linux on it, you can't do that on this. You have to run something and flash it directly to it. And I'm using the Arduino Ecosystem. There is another way of doing it where you're running, I think you can actually run Lua on it, MicroPython. There's a few different things there. But I use the Arduino Ecosystem because there's the most information about it out there. So Arduino Ecosystem is basically C. And the interesting thing is I've been programming since I was 9 years old or so, and I never learned C, and I think I'm probably in the minority here. I learned Pascal, which was a useful thing. No one has that anymore. Great, somebody did. So basically, Arduino is C++ with some libraries, and they don't call it that because I think people get afraid of C. And I thought, can I run Redis, which is kind of the de facto C client library, and I was disappointed that you can't do that. The problem lies in not memory or anything like that, which I thought was going to be the problem, but rather the stack in which you interface the IP, the Internet Protocol on it is completely different. So on the ESP8266, there's some RAM built in. It has RTOS, real-time operating system. Some people may have heard of that, but it says operating system in it, but it's not. It's more of like a BIOS. That's probably what the best analogy is to it. And I think it's like 48K of entire. Like that's how big it is. It's tiny. There's not much to it. But that's how the Wi-Fi is managed on this chip, and it doesn't use any of the same metaphors as Redis uses on Linux or Unix type environment. So that was disappointing. I thought I could just port it over and then start and go. No, that was not allowed. So we'll talk about RESP then. How many people have RESP? 2 people, good. RESP is interesting, right? I think RESP is Redis's secret weapon because it is the protocol that underlies Redis. So when you are talking with a client library, you're actually using RESP in the background. It's a really simple protocol, and I have worked with it a little bit. I am one of the maintainers of the node Redis client library, and I thought, okay, I can do this, right? So I decided to build a REST parser and serializer in a language that I didn't know, and I had a weekend to do it, and that was enough time. REST is quite simple, and it's quite elegant. So the great thing about it too is when you're dealing with 96K of RAM, you really need to be mindful of like even things like a HTTP header is pretty big. It's a lot of bytes actually. So REST is very easy. I mean, you're talking about 1 or 2 bytes of overhead when you're really looking at stuff like this. So here's the basic way REST works. You connect to your Redis server. You establish the IP and port you need to go to. You send bytes. It's the size that matters. So you have like I'm oversimplifying this, and there's a single page on redis.io that you can read in 5 minutes, and it describes the entire protocol. But basically, you have a couple symbols, and then you have the number of bytes, and then you send those bytes, and then you wait for a response. And it uses the same type of format. So it says, I have, let's say that you're sending something like zadd, or no, let's just do something easy. Keys, you should never call this, but I'm going to, especially on 96K of RAM. But you could do keys, you'd send it, say it's like 4 bytes, and then it'd come back and say, I have 1,000 bytes for you. And then that's how it works. Pretty simple, really elegant. So, and I like to call it just loop and wait, right? So here's the challenging part for me. Let's see if I can do this, if I can drag something over. I'm going to show you the code that I had to do. I wrote a serializer and parser. I wouldn't call it a client library because it's, that would be overselling it quite a bit. I just tried to get something that would have the most basic things that I needed. And that would be, you need to authenticate in. You should always have a Redis server that has an auth string. If you don't, then you're just waiting for a problem. I need to authenticate in and send one value and then just go to sleep. And so with that, I'll just see if I can get this over here for you. I'll just kind of describe what you have to do. You basically init, and then I'll put, there's where you can find all this source code. You init your object, and then you say, I'm going to send auth. You put in all of the arguments that you have, and then you send it, and then you just wait for something to come back. That's all you have to do. And so there was the auth thing, and that's the pretty easy one. And then on top of that, what you're going to do is use zadd. And so this particular thing is basically just a temperature logger, right? Real simple. And it's funny, when I was listening to Salvatore talk, he was talking about using sorted sets as a time series database, and he called it, quote, abuse of the data structure. And that's exactly what I was doing. So that was fun to hear right before my presentation. But basically what you do is, in this case, you're going to put everything, you're going to zadd. The first argument is going to be 0. And then you're going to have the UNIX timestamp, which I retrieved through UDP. And it will be, then you put a colon and then your temperature. And what's great about that is when you have that, you can use lexical sorting and you can get out the right times and divide things out. It's pretty easy for that. So in the future, like 4.2 comes out, I think streams would be the way to go. And then, once you have that, and you just wait a particular interval. In my case, we're talking about this example of the Icewine. Maybe you measure every, 5 minutes or something like that. So it's a pretty long actual delay time. So that's the basic long and short of the article that I wrote on Medium, right? But the idea never left my mind. And so I started thinking about some of the problems with it. Now, on my first generation, I was hard coding everything into it. So the auth string was hard coded into the source code, and that means that anytime I want to change my authentication string, I'd have to go, in this example, this theoretical example, go pull down these boxes from trees and hook them up to the computer, and that would never happen. So let's make it a little more practical. That's the auth problem, right? It's a really bad idea to hard code much into your software. I'm sure everybody has experienced that at some point in their careers. And as well, if you go in and somehow send that auth string to a device, then that's a problem as well, because at that point, you have given someone the keys to your kingdom, and you don't want that. So the other thing that you should keep in mind is Redis is not a multi-user database. It's a single user. Anybody who has access to anything can flush DB and ruin your night. So what I came up with was a very simple kind of way to protect the auth string. You have A, which is a prefix of the auth string that is hard-coded on the device, and a B, which is the rest of the auth string that you can change at will. So that way you're never actually releasing everything. The nice thing about the ESP and the Arduino ecosystem is it's really difficult once you flash something on here to extract it back out. So that's fairly secure there. So your part A is pretty well taken care of. And then the other part of the security in this, and I'm just, if you're a programmer worth your salt, you're obsessed with security. I renamed all my commands. In the RedisConf configuration file, you can go in and rename commands. And what I did is I renamed everything to random characters and a sufficiently long random character, which would be really difficult to brute force. I think that I did the calculation, it would be 624,000 years if you had 1 million operations per second. So, probably people aren't going to put that much effort into ruining your harvest, but you never know. So that kind of limits the damage to be done if someone could theoretically get into your system and get into Redis. So this is Authentication Flow, right? So this just second generation of this board that I built that is the temperature logger is a little more complicated circuitry-wise. This is the temperature probe. This is a slightly different ESP module, and it's got a big red button. This is the configuration button on it. And this means this will unlock things where you can go in and put your credentials in. That would be the Wi-Fi credentials and things like that. So to go and get your authentication information, which would be a few different things you'd need, the part B of the authentication string, and the zadd alias, because we renamed the commands. I'm going through and using an HTTP request at this point, which I tried to avoid, but I don't think there's a way around it. I built a small AWS gateway, API gateway, and Lambda script that goes through, accepts a username and password, and then returns back the requisite values, right? And that just gets this, and it's a very predictable amount of data, so it's pretty small. It shouldn't give you any crazy things. So then you're loaded in, and you have in RAM, you have the two parts, the A and B, which means allows you can auth into the system, and you have what zadd is, which is the only thing that we're going to use, the only command we're going to call, and it's a big long 30-character string that would be hard to guess. And so you go in and you request the data. You go to UDP or to NTP and get the time, and then you go through and you measure the temperature, which takes about 2 milliseconds, and then you record it to the server, and it falls asleep and goes away. So there was actually quite a bit of work going into getting this whole system set up where you have everything in such a constrained environment. It does take a lot of power. The thing you run into the most is SSL negotiation is really a stretch for this particular processor. Right now I'm using the SSL fingerprints that you can pull down from an SSL cert. And that's being hard-coded on, but there is a way to calculate it. But I'll get to that in just a second. So let's just talk about what can go wrong when you're trying to secure something like this. Quite a bit. I mean, it's not perfect. I don't think I would base a consumer product based on this whole setup, but it'd be good in a relatively controlled environment. So brute forcing, like I was talking about before, you're talking about, if you go to the brute force calculator, anywhere between 624,000 years to forever man, which is the kind of calculation they do for brute forcing random strings. So that's pretty good. I think that would be really difficult. I don't think that's a viable method of attack, but people can be really, really persistent. So masquerading as a device would be interesting too. So you do have to connect to a specific URL and then get your HTTP request. You'd have to have a username and password that's submitted to that. So that would have to be the security outlet that would, you'd then be granted as a particular user, so you'd know who's doing this. And it would, the URL is hard-coded on here, so it would be difficult to extract because, like I said, once you flash, it's kind of a one-way process on these devices. So it would be difficult to bring them back out. Additionally, what you're doing is you're recording it at a particular thing, like a serial number, for example. So a big, long, randomized serial number would actually give you a little bit of extra protection. So if someone was to come in and get into it, maybe they could change the access for one particular tree, not all the trees, in this example. Stealing credentials from the device, extremely difficult because of flashing. The other thing you can do in a situation like this, you could definitely go through and basically cut the data cords to the USB UART, and then you'd have almost no way of stealing something from it because you're just supplying power through USB in this case. Of course, then if you're going to flash, you'd never be able to flash it again. But these are so cheap, you just throw it away, crush it, do whatever you want to, run over with a car. The other good thing is that once you have this username system, you can block a particular device. If somebody is being really, a particular user especially is being abusive, you'd have that type of data and you could make those blocks and that sort of thing. So that's the presentation I wanted to give. I wanted to show you a couple things, and the setup's a little bit weird here. So I'm going to kind of lean over and try to show you a couple of things. This is the circuit that I used. If you can see here, this is, there's the ESP8266 on the one side there, and then the DS118B20 is the actual temperature probe right here. It uses what's called the one-wire protocol. And then up here you have, this is the article it was originally based on. I'm using zadd, and to get the data I'm using zrange by Lex, which is a great, really useful command for time series. But evidently it's abuse of the data structure. Okay. This is the web app that I wrote that logged it, and I want to talk a little bit about this. This is actually my dining room. So what I did there is, you could see this is from day to night. You could see the number of minutes. This is based on the timestamp, and it listed it there. And this is when this over here is where I actually grabbed the temperature probe, and it shot up like that. And so I actually learned quite a bit about this. And the other thing I want to talk about real quick is the scrambling the commands. If you can see here, I talk a little about in this article, rename command, and yeah. So I'm going to go back and then we'll talk about any questions that you guys might have. So open up the floor now if anybody wants to ask any questions. Oh yeah, I forgot to tell you, that was my last thing. So how I set my desk on fire. So what happened was, you get all this stuff, right, to do microcontrollers. You need a soldering iron, you need a power supply, you need all this stuff. And it all comes from China if you are trying to save a few bucks, and I was. And so with that, things come in really slowly. Some things will come immediately, some things will come later, and whatever. And I didn't have the particular cleaning device for my soldering iron. And I know that you could use steel wool for it, right? So it's there on my desk. And steel wool, if you've ever looked at any survival documentaries, are often used to start a fire. You took a 9-volt battery to it and it'll just instantly burst into flames. But I had unplugged my soldering iron and had left the power cord on the table, which is connected to the wall, producing like, I think 5 volts at like a pretty good amperage. And so when you're working with microcontrollers, it takes a long time to iterate. So when you're like writing code, you flash it to the device, and it takes maybe a minute to do that, and you realize it doesn't work, and then you go back and you write some more code, and loop and loop and loop and loop. And then so I was working on some code, and I had a really long desk at this place that I was just in, and my soldering iron was unplugged, I was being safe, and I realized that my steel wool had become magnetized. And that could actually really happen because steel is really easy, especially when it's a really thin filament. It can get magnetized really quickly. And it had attached itself, just one little wire had attached itself to the positive and negative of the power supply on my soldering iron. And I look over and I see this conflagration on the other side of me, and I go, this is a bad bug. And I run and get I had the forethought. I can't believe, usually I just panic and freeze, but I took some pliers and was able to take the flaming steel wool, drop it in the sink in the bathroom and turn it on and that. So yes, I was concentrating on Redis, trying to figure out how to write this parser, and I decided to make a nice big scorch mark on the desk in the house that I was currently selling. So that was fun to explain to the new owner. It wasn't there when you went to the house, but now it is. Yeah, it's very dangerous, right? It's dangerous, especially it can cause fires. But yeah. So that's how I caught fire to my desk working on Redis. Any other questions?
You had the REST protocol running on the microcontrollers,
right.
But where were you hosting Redis?
Right. In this case, I was hosting it on my development machine in a virtualized environment. But it could be anywhere. In fact, the original version, this was actually running on Redis Labs. So this was connecting to Redis Labs, doing all the authentication and coming in, and just the Redis Cloud service. So it was a little quicker to iterate through and to get my configuration file up and running. So yeah.
Because I was thinking you could potentially do some security around the network if you ran everything locally yourself.
Yeah.
And then you can also secure it that way.
Yeah, that's a good point. Eventually I'd love to work some more on this. Is it ready Redis as a platform for IoT? Not yet, but I think the REST protocol is a great fit. I think there would have to be some advances in how we think about security in Redis before I would put something out in the wild in a million consumers' hands.
Last question. You may not be the right person to ask, but in the user community, in the open source community, is there, do you believe, a forum or an opportunity to create some sort of open source project where we could start driving some of the requirements and having some dialogue and that sort?
Oh, I think that's great. I think that's something that's needed because I think I've written about 40 articles on Redis through my blog and things like that, and I think there's a lot of information out there for people, how to run a Redis server, and I think when we're talking about applications, and that's where there's a lot of place for the open source community to really go from there. I'd love to see, more mature things in the Arduino ecosystem for it. So yeah.
Thanks a lot, Kyle. That was a great presentation.